In 1997, I made a bet with John Preskill at Caltech, and the wager was an encyclopedia. Preskill claimed the universe keeps perfect records, while Kip Thorne stood with me on the other side, betting that black holes can truly erase information and delete it from existence as if it had never been. An encyclopedia seemed like fitting stakes for a debate about whether knowledge can be permanently destroyed, and for 30 years I believed I had found the one place in the cosmos where the past could be wiped clean. That belief turned out to be wrong, and understanding why it took me 3 decades to accept that reveals something unexpected about black holes, the structure of space-time, and the deepest puzzle in physics. Cambridge, where I spent my career, became the place where this question consumed more of my thinking than almost any other problem I faced. Most people picture black holes as cosmic vacuum cleaners that pull in everything nearby, and that image captures something true while missing the real strangeness. A black hole is not a thing in the usual sense, but a consequence, the result of what happens when gravity wins completely. Take any object and compress it into a small enough space, whether a star, a planet, or your own body, and gravity will overwhelm every other force with absolute dominance. The matter collapses beyond anything our equations can describe, leaving behind a region of space-time so severely curved that anything crossing its boundary faces only one possible future, which is inward toward the center, with no possibility of return. John Wheeler gave black holes their name, and he understood what that boundary means. We call it the event horizon, and it is not a surface you could touch or see, but a point of no return written into the geometry of space and time themselves. Cross that threshold, and every path forward leads to the singularity, because even light traveling, as fast as anything can travel, cannot climb back out. Physicists believed for decades that black holes were remarkably simple objects, and once something fell past the horizon, it was gone with no detailed records kept. A black hole formed from the collapse of a massive star would be identical to one formed from the collapse of 10 billion tons of encyclopedias, provided both had the same mass, charge, and spin. All the complexity and detailed information about what went in seemed to be stripped away completely. The no-hair theorem became famous for capturing this idea, stating that everything making objects distinct, including their composition, history, and structure, gets erased at the horizon. Black holes remember only 3 numbers, and everything else vanishes. That should have troubled physicists more than it did at the time. Quantum mechanics demands something specific about information, and the equations governing particles are reversible. Run them forward and you predict the future. Run them backward and you recover the past. Information in the deepest sense cannot be created or destroyed, but only shuffled, rearranged, and transformed, which means the universe maintains perfect records according to quantum mechanics. Black holes that truly erase information would put gaps in those records, and the universe would develop amnesia. Most physicists assumed for years that this was not a genuine crisis, because the information was merely trapped inside the black hole forever, hidden from the outside universe behind the event horizon. That seemed inconvenient, like a library book that can never be returned, but not a fundamental contradiction. And that's when I discovered something that transformed the problem entirely. The year was 1974, and I was at Cambridge working on what happens when you apply quantum mechanics to the curved space-time near a black hole's horizon. Jacob Bekenstein had already suggested 2 years earlier that black holes must have entropy, which is a measure of hidden information, and I initially resisted his idea because it seemed to violate thermodynamics. Black holes with entropy must have temperature, and black holes with temperature must radiate, but black holes by definition let nothing escape. My goal was to prove Bekenstein wrong, and instead I proved him right while discovering something neither of us had anticipated. Black holes glow, which means they are not completely black. Empty space, according to quantum mechanics, is not truly empty, but seethes with activity, as pairs of particles constantly flicker into existence. These particles borrow energy from the vacuum for the briefest of moments, and then annihilate each other to repay the debt, normally leaving no lasting trace. But here's the thing about what happens at the edge of a black hole's horizon. A particle pair is born, and before they can reconcile, one partner falls inward forever while the other escapes to freedom and becomes real. From the perspective of a distant observer, the black hole appears to emit radiation constantly from everywhere around the horizon, glowing with a faint thermal warmth. The temperature follows an elegant formula now called the Bekenstein-Hawking entropy relation, and I calculated that it is inversely proportional to mass. 60 nanokelvins is the temperature of a black hole with the mass of our sun, which is 100 million times colder than the cosmic microwave background filling all of space. You could never detect such a cold object's radiation against that pervasive warmth, like trying to see a single snowflake against a blizzard. Smaller black holes burn hotter, though, and a black hole the mass of a mountain would blaze with the heat of our sun, while one the mass of a large asteroid would outshine a nuclear explosion. The radiation carries energy away, and what that creates is the real crisis. Mass and energy are equivalent, as Einstein taught, which means the black hole loses mass as it radiates and shrinks over time. The timescales make the current age of the universe look like an eye blink for large black holes, but the process is inevitable and accelerates as the hole shrinks and heats up. A black hole in its final moments would explode with tremendous energy and then evaporate completely with nothing left. Everything that fell in over billions of years, every star and planet and piece of information that crossed the horizon, has to go somewhere. The radiation I calculated has a very specific character that is thermal and random. Like heat radiating from a warm stove that carries no message and encodes no structure and contains no information about what the stove was made of. Radiation from a black hole formed by a collapsing star would be identical to radiation from one formed by collapsing encyclopedias, which meant every trace of what went in would be erased. That led me to a dramatic conclusion I defended in papers, lectures, and in a brief history of time, stating that black holes destroy information permanently and irreversibly, while the universe forgets. What that means, if you stop and think about it, is that if information can be destroyed, the past becomes disconnected from the future. The laws of physics lose their reversibility, and the equations of quantum mechanics that had never failed would be incomplete. The universe would become fundamentally and permanently unknowable, not just unpredictable in practice. Leonard Susskind at Stanford refused to accept any of this, and for years we debated across papers, conferences, and letters. He insisted I must have made an error somewhere, and that a more complete calculation would reveal the information escaping, and I understood his discomfort but could not see how he could be right. The mathematics seemed clear to me. Confidence filled my thinking when I made the bet with Preskill and Thorne in 1997 because information falls in, gets scrambled at the singularity, and the random thermal radiation that comes out preserves no record. The universe has a shredder at its center, and that shredder truly destroys. None of that turned out to be true, but it took remarkable theoretical developments to show me why. The crucial insight came from thinking about black holes in an entirely new way by imagining how to describe a black hole not by its interior, but by its surface and what happens on the event horizon itself. Gerard Hooft developed this approach, and Juan Maldacena at the Institute for Advanced Study later formalized it into what we call the holographic principle. A hologram encodes three-dimensional information on a two-dimensional surface, and perhaps all the information about what falls into a black hole is encoded on its horizon in the same way. Black holes in this picture are not shredders that destroy documents, but the universe's most paranoid encrypting algorithm, one that does not delete your data, but scrambles it with a key so complex that cracking it would take longer than the cosmos will exist. The radiation is not truly random, if this is true, and it carries subtle correlations and complex patterns that encode everything that fell in. The information is scrambled almost beyond recognition, and trying to reconstruct it would be like trying to reconstruct a shredded document after the shredder burned the pieces, scattered the ash across a continent, and mixed it with the ash of every document ever shredded. That is the decryption problem we face, one that is theoretically solvable, but practically impossible. Don Page calculated something remarkable about this process by showing that information does not leak out steadily from the beginning. More than half of the black hole's mass has to evaporate before the escaping radiation begins carrying meaningful data, which is like a library that must burn more than halfway down before the smoke starts encoding the books. Before the page time, as we now call it, the radiation tells you almost nothing, and after it the information pours out but still encrypted and scrambled beyond any practical hope of reading. Dublin in 2004 became the place where I stood before my colleagues and conceded because the evidence had become overwhelming. New calculations, frameworks, and mathematics all pointed to the same conclusion that information survives, and I had been wrong for 30 years. John Preskill received his encyclopedia that day, which was Total Baseball, the ultimate baseball encyclopedia containing information about every game ever played and every statistic ever recorded. And that seemed like a fitting symbol for the idea that data survives. Kip Thorne has not conceded, though, and he remains skeptical that the theoretical arguments are conclusive, but the weight of evidence persuaded me. What changed my mind had nothing to do with philosophical discomfort about losing information, and everything to do with improved mathematics. Combining quantum mechanics with gravity more carefully than I could in 1974 using tools from string theory, the holographic principle, and Maldacena's correspondence between gravity and quantum field theory reveals that radiation from a black hole is not quite thermal. Subtle correlations exist between particles emitted at different times, and these correlations carry information. The information comes out incredibly slowly and in an unimaginably scrambled form, requiring you to collect virtually every particle a black hole ever emits over its entire lifetime. The calculations needed would be so complex that no computer that could ever exist would complete them before the universe ends. For any practical purpose, the information is lost, but in principle it survives. New puzzles emerge from this resolution that we still do not understand, including how information gets encoded on the horizon, if that is where it goes. When you fall into a black hole, you either experience your information being smeared across the horizon, or you sail smoothly through into the interior, and the equations seem to say both while both cannot be true. The firewall paradox carries this name from a 2012 paper by Almhiri, Marolf, Polchinski, and Sully. And it asks whether a wall of high-energy particles incinerates anything that crosses the horizon, or whether the horizon remains a gentle boundary you would not even notice crossing. We do not know the answer, and finding it may require a complete theory of quantum gravity we have not yet discovered. Something about the nature of reality itself becomes clear through all of this. Information used to seem like an abstraction, a concept humans invented to describe patterns in the world. But quantum mechanics teaches something different. Information is physical and as real as energy and as fundamental as mass, which means the universe is made of information at its deepest level. That information cannot be created or destroyed, but only transformed, rearranged, and encrypted. Black holes are scramblers rather than destroyers of information, and they are the most powerful scramblers in the universe. They take ordered information and randomize it more thoroughly than any other process we know, but they do not delete it because they cannot, since the laws of physics forbid it. What this tells us about the architecture of reality is remarkable because even when matter is crushed beyond recognition and space-time itself is warped beyond our equations, the information persists. It is encoded in correlations, in subtle patterns, and in the delicate structure of radiation that takes longer than the age of stars to emit. The universe keeps perfect records that cannot be erased. Black holes fascinated me throughout my life, not because they destroy, though from any practical standpoint they certainly do, but because they reveal the deepest connections between gravity, quantum mechanics, and information. Understanding black holes means understanding something fundamental about what reality is made of, and the question of whether information survives is not academic philosophy, but a question about whether the universe is consistent with itself and whether the past truly determines the future, and whether the laws of physics can be trusted? Absolutely. The answer we now believe is yes. Every event leaves a trace, and every action is encoded somewhere because the universe is faithful to its own rules. Nothing is truly forgotten, but only encrypted beyond any hope of reading. And that is what black holes have taught us. They are not cosmic erasers that delete the past, but cosmic vaults that hold everything that falls in, scrambled beyond recognition and encoded in the faintest radiation, preserved for eternity in a form we can never hope to read, but that exists nonetheless. The laws of physics do more than describe what happens because they guarantee that nothing is truly lost. When I made that bet in 1997, defending what seemed like the simplest interpretation of my own discovery, I thought black holes were simpler than quantum mechanics. The universe turned out to be more subtle than I imagined and more faithful to its own principles than I gave it credit for, with every equation balancing, every transaction recorded, and every piece of information surviving somewhere in the structure of reality, no matter how thoroughly scrambled. That is the lesson of my life's work, and what black holes have been trying to tell us all along.